first of all, okay, let me congratulate you. Most of you were able to take the online quiz without a problem, without any issues. So that's what you can expect in the future. There's going to be one at the end of this week as well. As we head on here, we're getting out of minerals now and heading into rocks. And what I wanted to say was there's a couple of things that I didn't convey to you that I really wanted to get across to you. Recall, and this is going to be probably an exam question as well, what are the 5 parts to the definition of a mineral? Remember, it has to be naturally occurring, inorganic, has to be a solid, has to have a crystalline structure, and then it also has to have a certain chemical formula. So, when we do these sort of like definitions like this, oftentimes we will pull out some examples. And so let me give you a couple of examples here, actually. Here's one of them right here. This is a rock. It's a volcanic rock, in fact. It's called obsidian. And this is a special variety of obsidian called snowflake obsidian. Now, snowflake obsidian, a volcanic rock, you would expect it to be made out of minerals, right? But if you look at it closely, look at it very closely there, you'll actually see a sort of glassy appearance, for most of it anyway, except for the snowflake part. And that glassy appearance tells us something. It, in fact, has conchoidal fracture, a lot like quartz has, but in fact, it's made out of glass. And so being made out of glass, so what is glass is the question then. As it turns out, glass is an amorphous substance. And in fact, there's a lot of different compositions. You can almost melt anything and turn it into a glass. Even carbonates, you can do that. That happens in meteorite impacts. So when you take a mineral and you turn it into glass, you break the bonds. And so it is a substance that we say amorphous, means without shape, but it also has no crystalline structure. So even though it's naturally occurring, it's a volcanic glass. It is a solid, no doubt. It's not organic, right? So it's inorganic, but it doesn't have that crystalline structure. And so because of that, it fails the mineral question. So you're going to find that there's a couple of rocks that are pretty common, but they don't meet the definition for being made out of minerals. Now that said, you'll also notice in snowflake obsidian that there are snowflakes in there. You know what those are? Those are crystals. Those are the crystals that begin to form through time, because sometimes you can get order from chaos, as it turns out. And so these are where the volcanic glass has devitrified. In other words, it's turned from glass through time into something that's a little bit more structured. And those snowflakes are actually where minerals are forming in that rock in a very, very slow pace in a solid state. And so, but that's snowflake obsidian. So obsidian, in other words, is a glass, and it's not a mineral. It's not made out of minerals. So that's an important thing to state. The other thing, because we're going to get into obsidian, we're going to get into some more igneous rocks here just briefly. There's another one that I have in mind as well. Ice. Ice is naturally occurring. You know that this time of year. It's on the tops of ponds. It's on the tops of puddles and things like that. It's on the roads, you know, so you have to be careful how you drive. We try to get rid of it if we can, right? But it gets on trees and everything else, right? And naturally occurring. Is it inorganic? Well, yeah. It's like water is not alive. It's not been alive. Even though it's in living creatures, it is not alive itself. Is it a solid? Well, ice is solid. Does it have a chemical formula? Well, yeah. It's the same as water, H2O, right? So water and ice are like this. If you get the right temperature, it's going to crystallize. So in other words, ice could be regarded as a mineral. Now, most people don't regard it as a mineral, not one that you want to study, because it's just too common, right? So it's like, but ice meets the definition for a mineral. So in other words, it has a crystalline structure. Well, what is that crystalline structure? You may wonder that, right? So that crystalline structure, once again, back to the word snowflake. So there are 6 angles, right? So 6 little arms that can go off of a snowflake. And that's because it's H2O, so there's a water, and they link up, and so, but they form that sort of crystalline structure where it's about 60 degrees in between the angles on that. And so that, in fact, is its crystalline form. So, in fact, ice meets the definition for a mineral. And that's all I wanted to share with you about minerals and wrap up minerals and tell you you did a pretty good job on the quiz. And so that's what you can expect in the future. There's no way I can, it was open book, right? So it's like, there's no way I can telegraph, what these things are before I give them. But at the same time, it's like, I just want you to make sure that you watch the videos and make sure that you get the readings done and make sure that you go to lab. And so in other words, and then if you read, in the book and you read the notes and you get all of the information, it's like, hopefully you'll retain some of it up here. And so that's what this is. It's a check on that to make sure that you retain some. So there's going to be one at the end of this week on the things that we cover this week. And so this will be part of the first video. And so we're going to talk about the rock cycle next. So we're going to talk about the rock cycle today. And it's important to remember that as human beings, we always look for explanations for things. And so we do that in the Western culture all the time, and oftentimes we rely on science in order to help us understand the natural world. For the ancient past, it was a little bit more difficult, right? And so it's pre-science sort of days, but, let me give an example here. So what you see in this photograph is a place called Devil's Tower. That's, the English name for it, right? So the American name for it. But it's actually the interior of a volcano. That's our explanation for how that rock came to be there. And then also how it has these sort of like columns that comprise that rock. When people were looking for an explanation before, the white settlers arrived in this area, Native Americans looked for explanations as well. Their explanation for this area, and it's no less crazy than what some other folks have said, it's that there at one time was a giant bear that crossed this landscape. Now, this is in northeastern Wyoming. It's a place that is almost flat for the most part. If you went east from here just a little ways, you'd be in the Black Hills of South Dakota. This in Wyoming here, and what you can see here is the legend. And so the people, that is the Cheyenne Nation who lived here, were accustomed to seeing this, and they camped around the base of what we today call Devil's Tower. And so the people, that's their name for themselves, the Cheyenne, had trouble with this bear for a long time. And so they looked for a way to escape it. And so they went to the top of this tower. And so what you see are these striations, these columns essentially, and they're huge, right? So these columns are actually 5 or 6 feet across, many of them anyway. And so it's still a sacred site for the Cheyenne. It showed it was the salvation of the people. And so this giant grizzly bear who had roamed the landscape was clawing. And so that's what you see are the results of that clawing when you look at this. And so that's the legend that they came up with to explain that. Well, they explained it to their kids and everything back at the time. So that is the Cheyenne Nation's legend for the origin of Devil's Tower. And today, we use science today, right? But it's a very quaint, a very ingenious sort of like idea to equate the grooves with like the claw marks of a giant bear. And so it seems to fit. So as we look for explanations, one of the things that you've probably been introduced to already, probably as early as grade school, is that there are 3 rock types. And so I'm going to repeat it one more time here. And that is that there are igneous and sedimentary and metamorphic rocks. And so igneous rocks are fire-made. So like you would ignite a match or, anything that catch it on fire, that is igneous, and that's where where the phrase comes from. Sedimentary rocks, in fact, are composed of particles that have been cemented together, or they were maybe once alive, some of these things. So like fossils, for instance, could get incorporated into sedimentary rocks. And so sediments have to come from somewhere.
Those sediments very commonly are a result of uplift and erosion of igneous rocks, as it turns out. Most rocks that are sedimentary in their origin actually started either as metamorphic or as igneous rocks. And so lastly, the third type of rock is metamorphic, and metamorphic refers to change. And so if you can heat rocks up, or if you can pressurize them, or if you can expose them to shock pressures, that's going to do something we call metamorphosing the minerals that are in that rock. And in fact, it changes their shape, and it changes sometimes even the type of mineral it is. It can even change their composition. So metamorphic rocks are the third variety. So we're going to talk about each one of these in pretty good detail. So the processes we're talking about, in fact, include crystallization. Sometimes you have to crystallize minerals out of a magma. And so we'll talk about the crystallization process. We'll talk about uplift and exposure when we get to sedimentary rocks, because we have to uplift and then expose these igneous rocks or the metamorphic rocks that are buried at depth at some point, and expose them to the Earth's elements in the atmosphere. And so when that happens, you get weathering, you get transportation of those particles, and then you get deposition of those particles. And eventually they're going to lithify in some way. They either may be compacted or they may be cemented together. And that happens during a burial process. In other words, sediments come to rest in a basin at some point, and in that basin they get more and more sediments heaped upon them, and eventually they're going to become cemented or compacted. If we bury it deeply enough, or if we expose it to high temperature or pressure, as we said with metamorphism, you can metamorphose it as well. And eventually, if you can get it hot enough, you can melt it. And when you melt it, you can turn it back into a magma, which is where this whole process started in the first place. So they call this idea, it's almost like rocks can be, what's the term for it? Reincarnated? Yeah. So the rocks can be reincarnated from igneous to sedimentary, and then from sedimentary to metamorphic, and from metamorphic, if they're melted, they go back into a magma, and that magma can crystallize and turn into an igneous rock. And so those are the steps that you can do it. Now, you can take shortcuts in between, but this image right here shows you some of the various settings where those things occur. So for instance, a magma, a lot of people call it molten rock, but it's really not rock yet, right? It's still just molten material. Well, what's that molten material? Well, if it's not rock, what is it? It's an amorphous substance, like glass, if you will, and that amorphous substance is made out of ions. And those ions, eventually, when they come to rest and cool off, can crystallize, and they will become an igneous rock. And so that's the first step, is we have to have a magma first in order to form igneous rocks. And then we have to uplift and erode those rocks in order to get the sediments. And then the sediments can be deposited. So you can see how the cycle works here. And so it shows you all the arrows in which you could take, you can take a metamorphic rock and you can erode it. And you can take a sedimentary rock and you can erode it, turn it back into sediment. And so there's some loops in here that may go on for hundreds of millions of years and almost billions, some of them, right? So some of these rocks, it takes a long time for them to go through that process of reincarnation, if you will. So those are the steps that we're going to talk about in here. And the guy who came up with this, he was brilliant. He was a geologist. Well, he was one of the earliest geologists. He was a Scotsman. He was a doctor, actually, first, and so he trained to become a physician, but he didn't like to work with people. And so it's like he decided instead, I'm going to be a gentleman farmer. And so he farmed in southern Scotland. And eventually he decided he would go on vacations, and his vacations revolved around geology for the most part. And he understood igneous rocks for the first time. And he realized that, these rocks really did form from some sort of amorphous substance that we today call a magma. And so he recognized that. And he also recognized uplift and erosion. He recognized another feature too. So you're going to hear this name again when we talk about sedimentary rocks and the key principles in sedimentary stratification of sedimentary rocks. But his name was James Hutton. So James Hutton in 1785, he figured out everything but the metamorphic part of these processes. So that's in the 1700s. Oh my gosh, that's like almost 250 years ago, right? So 245 years ago anyway. Well, 235 years ago. And he figured that out. So when it comes to these rocks are all either exposed at the surface in outcrops, or they may be in road cuts, or they can be in quarries where people mine them, or you know that they're actually just below the surface as well. And so when anybody excavates, at least in Springfield anyway, they're going to eventually hit limestone down there. And so when they do that, you're actually exposing the rocks are at the surface there. And so another brilliant guy came up with in 1815. He was a working man. He had a company that dug ditches essentially to drain swampland, and he worked in Britain also. So if Hutton was from Scotland, William Smith was from England, and William Smith is what they called a jobbing ditcher. And so what he did is he drained these swamplands. And when he was doing that, he took careful notes and he collected fossils. And so some of the fossils that he collected, he saw them in other places. And it's like, I've seen that before. And as he collected these things, he began to take some notes. And then eventually he made the first geologic map. So if you stripped away all of the soil of Britain, this map is a representation of the kind of rock that you would see in the subsurface, and it's a geologic map. William Smith made the first geologic map and published it in 1815. So he kind of overlaps with Hutton a little bit, but they didn't know each other. Hutton was a gentleman. Smith was a working man. And so, but he came up with this brilliant idea to map the geology of England, Cornwall, and Wales right here, and the southern part of Scotland as well. And that's what you see in this map. So, as you know, rocks almost always are composed of minerals, almost always. The exceptions are, at least for your understanding, are obsidian, which we talked about just earlier today, right? Obsidian is a volcanic glass, and so glass being an amorphous substance is not crystalline. And then coal. Coal is another one. Coal is a sedimentary rock, but it's made out of compressed plant debris. And so rocks comprise most of the earth, almost all of the earth, in fact, in the outer parts out here. And so, in fact, even in the mantle, it's made out of rock. So 70% of the Earth's surface, in fact, the rock that is there, 70% of it's sedimentary rock for the most part. There's a few isolated areas then that are igneous rock. Some of those are in Missouri, as it turns out. And so if you went to Farmington or to places like Ironton in Missouri, you'd be surrounded by the igneous knobs that comprise the St. Francis Mountains. Those are the high mountains that are in the eastern part of the state. So Tomsock Mountain, for instance, igneous rock. If you went to Johnson Shut-ins, or if you went to Elephant Rocks, those may be parks that you've heard of before. Those parks, in fact, are made out of igneous rocks. So they make these spectacular shapes and these fascinating landscapes that we see. So Shut-ins are a lot like river rapids, if you will. And we see all these igneous rocks, in fact, in just a few places around the world. So, but we're gonna dwell on them first. So we're talking about the rock cycle right now, but just know that some of the rocks you see in this map as well are igneous, and some of them are sedimentary, and some of them are metamorphic, as it turns out. Now, William Smith didn't know anything about metamorphic rocks either. It took until the late 1800s and the early 1900s before people figured that out eventually. And so they began to map then metamorphic facies in places where metamorphic rocks are exposed. So as we go farther along here, I want to give you an idea. Igneous rocks have a couple of different ways they manifest themselves or they express themselves. One of those is through the eruptions of volcanoes. And so right now on Earth, there are about 1,500 volcanoes, and some of those are erupting even as we speak. Kilauea is going off right now, and that's on the island and state of Hawaii, right? So in Kilauea, the caldera is beginning to fill with magma. Now, you might think that that's pretty safe, probably, because people are around it, they can film it and everything, but sometimes it can blow up. And so that's how you form the sort of calderas that Kilauea is. Kilauea is a caldera, and it formed from a massive explosion at one point. There are other ones that have exploded as well. The very same year that William Smith published his map in 1815, there was an eruption of a volcano in Indonesia. And here you can see on this map, that's Mount Tambora. And you see a photo of Mount Tambora, and you see the island that Mount Tambora is on here in the Indonesian archipelago. And so you can actually see that it's a pretty high mountain. And in fact, it blew its top back in 1815. It's a fascinating story about this. 1815, the eruption occurred. 1816, the following year, there was so much material in the Earth's atmosphere that it changed the climate for a short period of time. And we had what was known as the year without a summer in 1816. And in fact, that was the year, even in, how salt water usually doesn't freeze, when you're in the mid-Atlantic. The harbors froze over in New York City because there was such a climate change. And so it was a very, very cold period of time. And so these guys that were in Britain, they would have experienced a lot of cold as well. And so the year without a summer, there was a lot of crop failures and things like that. So in other words, it made a huge worldwide impact from this volcanic eruption. Now that's the biggest we've had in recent memory. And so Mount Pinatubo wasn't quite as big as this. Okay, so Mount Pinatubo in 1991, I think it was, when it erupted, it was a massive eruption as well, but not nearly so big as this. This one killed 92,000 people pretty much out of the block. So a lot of those were people that lived around the volcano, but then also there are people who starved to death because of that volcanic eruption. They had nowhere to go. So 90,000 people died as a result of that geologic process. It's a natural process, and people die all the time from these sorts of things. Okay, so if we went ahead, there's an older geologic map in the United States. We always like to claim that we do the first and the bestest and all that sort of thing, but that map had nothing to do with the same level of detail as what William Smith had. This was a map by William McClure, who also was a brilliant geologist, an early geologist. He lived on the East Coast, and he had traveled the eastern seaboard of the United States and some into the Midwest. And so he came up with this map in 1809. There is a Midwest connection for this guy, which is kind of cool too. And that's one of the reasons. So the Midwestern United States, he actually, and so you can see where his map stops in Illinois there. But this guy lived in Indiana for a short period of time. And so he lived in essentially a utopian colony where they decided to learn geology and astronomy and all the other things that go in the sciences. And so it was a scientific utopian society at a place called New Harmony. And New Harmony still exists. It's a little town in southwestern Indiana, a fascinating place. But William McClure lived there for a short period of time. So to wrap it up here, we have igneous rocks. And so some of those igneous rocks are volcanic in origin. The other type of rocks igneous rocks, in fact, are the ones that cool at depth. And so those we call plutonic igneous rocks. And so plutonic igneous rocks cool right in place inside of the earth. And so they don't have to be erupted, but they're made out of the same magmas that would have been involved in an eruption, perhaps. And so, in fact, what they do very commonly is they will actually cook the rocks around them. And that's what you see in this image. Now, that's one of my favorite places on Earth right here. That's a place called Notch Peak. And what you see here is the Notch Peak intrusive around this. Now, it actually forms a sill right here, which is a flat, tabular sort of shape to it. But it cooked the rocks around it. And so that's a limestone that's been metamorphosed. So limestone is a sedimentary rock. When it got around the heat, it got metamorphosed and turned into this rock. And that's called a skarn, actually. That's the typical name for that. They actually find gold around this sort of intrusion. So pretty important sort of things, right? So we're going to look at sedimentary rocks. We're going to look at igneous rocks. We're going to look at metamorphic rocks in here. And so that is the idea of the rock cycle. All of these processes bind these things together, and rocks can evolve through time. Rocks can kind of be, reincarnated through time as well. So that is the story of the rock cycle. And next, we're going to go on to volcanoes and look at some of the other igneous rocks. So we're going to look at volcanoes first, then we're going to look at plutonic igneous rocks, and from there to the sedimentary and the metamorphic. So anyway, that's it for now. Thanks a lot. Thanks for your attention. Bye now.